Hello guys, welcome back to Tuber Teaches. So today we're going to be doing another worked example specifically for the higher levels. I think I've given enough focus to the standard levels, but I think the higher levels deserve a bit more justice. So we're going to do question number 8 here, the whole thing. So pause the video if you want to try, pause the video if you want to try this yourself, and come back for the worked solution in a couple seconds. Alright, so I assume you're back. I'm only going to focus on the biacetyl bit because I'm sure the acetonin bit we can work on. That follows a similar process. So first, let's complete the Lewis structure. So C H H H C C C H H H double bonded O, double bonded O, and lone pairs there, lone pairs there. So this is part A. So that's part A done, and then now we predict the values for all CCO bonds. So all these CCO, CCO. So we're going to call this the central atom. So we call this the so here to make our lives easier, we're going to call this the central atom, and that has 1, 2, 3 electron domains. So, and we know that for 3 electron domains, their geometry will be arranged in a trigonal planar arrangement. So like here, let me just sort of draw this out. So let me focus on just that atom, particularly C double O. We can see here 1 domain, 2 domain, 3 domain, and this is trigonal planar. And again, you just sort of have to memorize that fact that, okay, 3 domains corresponds to trigonal planar, and trigonal planar corresponds to bond angles of 120 degrees, so 120 degrees. So yeah, there's that. It's 120 degrees between this C double O, and then since this is a mirror image, again, since this is basically, you could split the molecule up here. Again, we could do the similar thing. So C double O, and you would find the same thing. That is also 120 degrees. So 120 degrees for part B. For part C, we give the hybridizations of each carbon atom in the compound. So let me use a different color here. Let's use red. So there are 1, 2, 3, 4. 4 minus 1 is 3, so this is sp3. This is 1, 2, 3 domains. 3 minus 1 is 2, so this is sp2 hybridized. 1, 2, 3, so sp2 hybridized. And the way I'm doing that is just I'm counting the number of electron domains minus 1, and that is and that is just how many p orbitals hybridized, and you just slap an s on there. And then lastly, we have 1, 2, 3, 4, so sp3 hybridized. So there we go. That's part C done. Above. For part D, this one is a bit of a harder question to do. Basically, it asks, can the 4 carbon atoms and the 2 oxygen atoms in the biacetyl possibly be in the same plane? And explain. So can this, let me use green. Can this, and this all lie in the same plane? Well, in order to answer that question, we have to think a little bit creatively. We know that's trigonal planar. And we therefore know that since there are two trigonal planar things stuck to each other, they can. Since we know that those two trigonal planar things are there, we can make. Since we know that they all lie on the same plane of 2D space, or well, here, let me rephrase that. Let me try and phrase this in a way. They don't occupy all three dimensions of 3D space, because if you have a tetrahedron, right, that occupies the x, y, and z axis, whereas a triangle only occupies the xy axis or the yz axis or whatever. So maybe, so we could actually, so since they're both trigonal planar and they don't occupy all three dimensions in space, they only occupy two of them. The answer is conceivably yes if you lined up the bonds. And let me just show what that would sort of look like. Here is our sort of here, let me use a different color back. No, I don't want to save that. So let's use maybe orange. I'm trying to try this like as accurately as representative as possible, so this is sort of me trying to draw everything on the same plane. And then since these are tetrahedrons, so those are tetrahedrons, those are oxygen atoms. And we can see here clearly that the only thing that is not on the plane here is the hydrogen. So we can sort of, let's use our black marker again. We can clearly see here that if that was our plane of reference, they all lie in the same plane, whereas these hydrogens don't necessarily line up in the same plane. So the answer to that is the 4 carbon atoms and the 2 oxygen atoms can indeed be in the same plane. Now, this isn't always the case, because this bond here, since it's a single bond, it can rotate freely in space, but it is possible to get, it is possible that in some cases that bond can, all the atoms can lie in the same plane. So, to sort of recap what I did there to do that question, because it's probably a very hard question, you probably want to get that on an IB exam, but the way I did it is I considered the shapes of each central. I decided to call a few atoms central just to make my life easier, and I strategically chose the middle carbons. I then drew out the geometry diagrams, and then sort of I then drew out sort of what the structure would look like, accounting for molecular geometry on an XY plane, like that, and then I tried to do what the question asks, which is align them all on the same plane in 3D space, keeping in mind the molecular geometries of everything. So the answer to that question is yes, you could theoretically do that. So it does take a bit of practice to do, but once you get your head around the idea of 3D space and being comfortable with it, it really does make your life easy. E is just the same thing for the other molecules, so I will skip that. And then lastly, for F, we are asked how many sigma and pi bonds there are. So remember, each single bond counts as a sigma, and each double counts as sigma plus pi. So there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 sigma, and then remember, each double bond is, each extra bond after a single bond is a pi bond. So 1, 2 pi's. So 2 pi bonds. So yeah, that should do it. Thank you very much for watching. Don't forget to like and subscribe.